Hey, in this video, we're going to talk about piecewise functions, and we'll start off with a word problem. So a piecewise function, we're going to think about as a way to combine multiple functions into a single function, depending on what the x value is. And you'll see what I mean in a second. So this word problem is saying that we have an internet provider that wants a function to model the total cost based on the number of customers they have. So it costs them $10 to support a customer, and for every 30 customers, they also need to provide equipment for a transformer in the neighborhood, which costs $70. And for the sake of this problem, we're going to say they can only support a maximum of 89 customers. And we want to create a function that models their cost based on the number of people. So this gives us three cases. And these three cases are going to be split up based on how much equipment they have to buy for their transformers. So if customers is less than or equal to 30, then their cost is $70 plus 10 times the number of customers. So hopefully that makes sense, where if the number of customers is less than 30, we only have to buy one set of equipment. And we want to then add in $10 for each customer we have. So this, in economics terms, $70 is known as a fixed cost, and the $10 is known as a variable cost. Because, well, customers is less than 30, the cost that it takes per customer changes, but we still have to pay that $70 no matter what. If customers is between 31 and 60, then our cost is $140 plus 10 times customers, which again hopefully makes sense. Is the same argument with 10 times the number of customers, but now we have to buy two sets of equipment. That's $140. And if customers is between 61 and 90, so I guess we can just change this up here to 90. Then the cost, and the cost is $210 plus 10 times the number of customers. And if we're looking at a graph, our graph would look like this. At 0, we start off at 70. Because we have to pay that fixed cost of 70 no matter what. And then we have a slope of 10 going up. So this will be at 30 customers. And this price will be $370. So obviously this graph isn't drawn to scale, but for the sake of the problem, I hope it suffices. And then if we want to serve more people, we need to buy another equipment set for the transformer. So that's going to add $70 to the cost. So that brings us up to $440. And we get a dot up there, make a marking for 60. And for foresight, I'll put one for 90. And then we go up at the same slope. And so now we have 60 customers, so that's 600 plus 140, that's $740. And then we have to go up to 810 for when we have to buy the third transformer, and that goes up even more. So because we have these breaks, we can't find a simple function to model cost on its own. So what we need is to use a piecewise function. And so our piecewise function is a combination of these three different functions based on what our cost is. So f of x equals, we'll have 70 plus 10 times x. So we're thinking of x as the number of customers. 140 plus 10 times x, and 210 plus 10 times x. And then we do a little if, and that if is going to be followed by the condition. So if x is less than or equal to 30, if 30 is less than x is less than or equal to, sorry about that, to 60, and if 60 is less than x is less than or equal to 90. And that's our function. So if we plug in f of 20, we see that x is at 20, so we get 70, plus we look for the case for x at 20 is less than 30, so we're in the first case, we get 70 plus 10 times 20, and the total cost would be $270. But if we plug in f of 78, we would then be in the third case. So we'd have to be spending 210 plus 10 times 78, which is $780, $990. So that's about it for piecewise functions. We can think about the endpoint as just specifying a domain. And then if x is in one of those specified domains, then that tells us the function that we have to use. What we need to be careful about is that these regions don't overlap. The problem with them overlapping is that if they overlap, say an x is in the first one and the second one, then we would have to evaluate the function for both of those, and they could be two different outputs, which would break the rules of being a function. All right, so these economics ones are pretty easy to understand, but I want to go over a slightly more complex one that I think some of you will find interesting. So this is a piecewise function that came up when I was writing a master's thesis last year. So I was trying to write or trying to improve upon a model to model how electricity flows through cardiac tissue. And this is of interest to a lot of biologists who want to have working computer models of the heart. So the idea is that you could write a computer program that has a whole bunch of cells, or models a whole bunch of like literal heart cells stacked on top of each other, next to each other. And then you could simulate introducing a beat of electricity, or like a heartbeat. And then the heart would, some cells would contract when an action potential happens. So one thing that we needed is a way to model an action potential. So an action potential is a process of the heart that when the heart gets to a certain voltage, or sorry, when a cardiac cell gets to a certain voltage and action potential is triggered, the voltage shoots up in the cell because of something called ion channels, allowing sodium and potassium and calcium to move through the cell. And the cell itself contracts. So we want a model that tells us how electricity will change over time. And so what we can use is this piecewise function, f of x equals negative x and 1 minus x. This is saying that this model is good for when the resting voltage, which is 0, and the maximum voltage is 1. Of course, that's not what the true resting and maximum voltages are, but in mathematics, we find ways to simplify things. So there's a way to change the numbers around when you're actually working on these to make it so that the resting voltage is 0, the maximum voltage is 1. And that's a process called normalization, because we're making it something a bit more normal. And action potentials tend to look like this, where we're at 0 here, 1 up here. And you either have a little bit of change in voltage, and then it goes back down, or there's a resting threshold, which we call, or there's an action potential threshold called A. And if the voltage ever hits A, then these ion channels open up, a flood of ions rush in to the cell, and the voltage spikes really fast and tops out around 1 and then comes down. So we need a function that models the change in voltage over time. Time. So this axis is the voltage axis, and this is time. And the reason we're looking at change in voltage over change in time is this is a concept that comes up when you're studying differential equations. So theoretically, once you get to calculus, you could start studying differential equations and understanding more of this model. But so calculus allows you to look at how things are changing over time. And then that's a way to understand how the voltage is changing altogether. So our change in voltage over change in time is going to be modeled by this function, f of x right above. And the idea is that if we haven't hit this threshold potential, then our voltage should be decreasing a little bit. And so physiologists have found that just saying negative x isn't that bad. Because if you're close to A but not quite at A, then you actually decrease pretty quickly if you don't hit that action potential. So we get slightly larger values. So we get negative x for x less than a. And so because this is a negative number, it's saying that the change in voltage over the change in time is negative. So as time goes on, the voltage is going down. But if we exceed A, then we expect to spike up. So if we have this 1 minus, because x never exceeds 1, then the voltage is going to shoot up. This is going to be positive if x is greater than or equal to a. And as x gets closer and closer to 1, it slows down how fast it's changing over time. And once x has gone beyond 1, then it starts to decay again. So this is just an example of where piecewise functions come up in biology. For some of you, I would totally expect this to go over your head, which is completely fine. I just wanted to add this in as an example of somewhere else where piecewise functions come in. And I know we have a lot of nursing and medical students in this class who may or may not be interested in how math plays a role in the heart. All right, signing off now.